Mrs. Traver here. Today we're going to wrap up everything we've got about right triangles with Pythagorean triples. Our learning target for today is that you can recognize 3, 4, 5, and 5, 12, 13 triangles to find other Pythagorean triples. You know you'll be successful when you can use these shortcuts with Pythagorean triples to find side lengths in right triangles. Let's jump in, and I just want to show you 3 quick pictures, and let's see if we can find all the missing sides here. So usually how we do this, it's called Pythagorean triples, so it reminds me of Pythagorean theorem. Let's use Pythagorean theorem. We'd have a squared plus b squared equals c squared. So in this case, 3 squared plus 4 squared equals c squared. 3 squared is 9, 4 squared is 16, 9 plus 16 sums to 25. And if I take the square root, I've got a nice whole number. C is 5. Not too bad. Quick review. Let's do the next one. I've got, again, a and b given to me, and I'm looking for c. So I've got 6 squared plus 8 squared equals, this would be c squared. 6 squared is 36. 8 squared is 64. 36 plus 64 is 100. And the square root of 100 is 10. Let's look at the last one here. Do you notice anything similar with the last one compared to any problems we've done so far? To me, it kind of looks like the first problem, but scaled up times 10. Not times 10, I'm sorry, times 1,000. So it looks to me like this is a 3, 4, 5, and this one should be a 3,000, 4,000, 5,000. And that's actually the case. Matter of fact, the second triangle was the same triangle too. It was just 3 times 2, 4 times 2, 5 times 2. This will work for every triangle that has that relationship, where it can get pared down and divisible into a 3, 4 type triangle. Here's another set. Let's look at this triangle. It's got a 5, something, and a 13. So I'd have a squared is 5 squared. I don't know b, so b squared equals 13 squared. 5 squared is 25. 13 squared is 169. We subtract 25 from both sides, I'll have 144. And if we square root, we'll get 12. Here we are, a 5, 12, 13 triangle. This is similar to the last slide, so I want you to see if you could recognize the difference between this and the last one with our scale factor again. It looks to me like this bottom 5, the small leg, is now 15, so that was times 3. And then 12 times 3 is also 36. We can do the same thing for the last side now. 13 times 3 is 39. Quick cheat code for you is how my students in class call it. This one has a 5 and a 12. I know sides that have legs 5 and 12 have a hypotenuse of 13. This is pretty quick when we recognize those differences. Are there any more other than 3, 4, 5 and 5, 12, 13? Let's see. If we had a scale factor of 2, in this case our Pythagorean triple 3, 4, 5 would now be 6, 8, 10. If we did times 5, we'd have 3 times 5 is 15, 4 times 5 is 20, 5 times 5 is 25. Try the same thing with 5, 12, 13. I'd have 10, 24, 36, 26, not 36. And if I did times 5, 5 times 5 is 25, 12 times 5 is 60, 13 times 5 is 75. So you notice this recognized goes on and on. There are more, matter of fact. Here's a list of more of them that are specific. Notice like 6, 8, 10 is not on this list because it's actually a 3, 4, 5. And 50, 120, 130 is not on this list because it's also a 5, 12, 13. These are all specifically different Pythagorean triples, which is kind of amazing that these numbers all work out when you do Pythagorean theorem to be a whole number. So a lot of mathematicians over a lot of years have looked at this list and tried to find more. And it's actually been proven that there's infinitely many more Pythagorean triples, which is just mind-boggling to me. There's actually like a race to find the largest one, which we know infinitely means there's not a largest one, but it's kind of like a clout thing to have like the biggest one found. Let me show you something else, which I think is kind of cool. So here's a picture. You can tell here's a right triangle on the inside, and this is a 3, 4, 5 triangle. I can tell because this side is 3 with the boxes, this side is 4, and this side is 5. And I can actually make this bigger. So if I go bigger by a little bit, it'll take a minute to update. And it basically just cut these boxes. And now this box is 6, this is 8, and this is 10. And now let me get crazy. I'm going to move it over here. It just cut it a bunch of times. It looks like now instead of a 3, 4, 5, it went from 3 to 15, so times 5. So 15 by 20 by 25. And I can really just go for it and go all the way. Now they cut it, instead of a 3, 4, 5, it's now a 20, 21, 29. So all of these are variations of the same thing. And like I said, it's kind of amazing that, like, notice 20, 21, 29, it's actually not on this list that we had. Where'd it go? That's not the right slideshow. How about this one? It's not on this list we had because it's really just a 3, 4, 5, but been multiplied up. So there's so many of these combinations of numbers, but yet they're so hard to find. Let me show you the list of all of them. Well, not all of them, but a bunch of them. Here's where it gets crazy because this is as far as we've come. That's it, only up to 985. So it's kind of cool because we know there's infinitely many, but really we haven't found that many. I don't know. I'm geeking out, sorry. I just think it's kind of cool. With our last bit here, I just want to kind of review with you for a moment where we've come. So we have shortcuts with right triangles now. We have the 45, 45, 90 shortcut. We have the 30, 60, 90 shortcut. And now we have 3, 4, 5, and 5, 12, 13 shortcut. Each of these cases is an original triangle that can be scaled up or down by any scale factor and have the same relationship as its proportionate. Its angles will be the same, but the sides will stay proportionate. So that's what makes them cheat codes. I'll see you next time, guys. Have a good one.